For the first time in scientific history, researchers have made a 260-million-year-old fossil, here again through biomechanical simulation. Using cutting-edge computer modeling, scientists at the Smithsonian Institution have found evidence that an ancient reptile called Youngina capensis possessed advanced hearing capabilities that challenge everything we thought we knew about reptile evolution. The findings, published in Nature Communications in 2025 and accepted in November 2025, suggest that sophisticated hearing evolved much earlier than previously believed. Hearing evolution has puzzled scientists for decades. While mammalian hearing is well understood, with our complex three-bone middle ear system evolving from ancient jaw bones, reptilian hearing has remained enigmatic. Modern reptiles use a simpler system, with sound waves traveling from the eardrum through a single bone called the stapes to the inner ear. But when and how this system evolved has been one of paleontology's most contentious debates. For years, scientists believed that advanced hearing evolved independently in each major group of reptiles. Lizards, crocodiles, and turtles were thought to have developed their hearing abilities separately during the Triassic period, roughly 250 to 200 million years ago. Reference fossil ear bone comparisons from scientific literature. This hypothesis was based on observations that many Permian-era reptiles possessed large, bulky ear bones that seemed incapable of transmitting high-frequency sounds effectively. The prevailing wisdom suggested these ancient reptiles were essentially deaf to airborne sounds. What researchers discovered challenges this entire narrative. Meet Youngina capensis, a small reptile that lived in what is now South Africa during the Late Permian period, approximately 260 million years ago. Youngina was roughly the size of a modern lizard, measuring about 30 centimeters in length. Youngina capensis holds a crucial position in the reptilian family tree. It represents what paleontologists call a stem reptile, meaning it lived near the evolutionary split that led to all modern reptile groups. The fossil specimens of Youngina capensis have been studied extensively since their discovery, but the ear bones, or stapes, were noted but not subjected to detailed biomechanical analysis. These stapes appeared intermediate between the bulky forms seen in earlier reptiles and the slender forms characteristic of modern reptiles with advanced hearing. Dr. Kelsey Jenkins, Rachel Fleming, Juan Daza, and Hans Dieter Sues at the Smithsonian's National Museum of Natural History recognized that the morphology of Youngina's stapes suggested something remarkable. Rather than accepting the assumption that these ancient reptiles had poor hearing, they decided to test this hypothesis using state-of-the-art biomechanical modeling techniques. The breakthrough came through a technique called Harmonic Response Analysis, or HRA. This sophisticated computer modeling approach allowed the research team to simulate how Youngina's fossilized ear bones would have responded to sound waves 260 million years ago. This is a biomechanical simulation using harmonic response analysis, not literal hearing. The fossil cannot actually hear. The process began with creating highly detailed 3D models of the stapes from multiple fossil specimens. Using advanced CT scanning and digital reconstruction techniques, the researchers captured every detail of the bone's structure. These digital models were then subjected to virtual sound pressure of 2 Pa, approximately 100 decibels SPL, roughly the volume of a motorcycle engine. The computer simulations measured how much the stapes would vibrate when exposed to sounds across a range of frequencies from 100 to 10,000 Hz, with particular focus on the 100 to 1,000 Hz range that characterizes effective hearing in modern reptiles. To validate their approach, the research team first tested their methods on modern geckos with well-documented hearing capabilities. The simulations successfully replicated the known hearing characteristics of these living reptiles. For comparison, the researchers also analyzed the stapes of two much earlier reptiles, Captorhinus agudi and Bolosaurus major, both from the early Permian period. These earlier species showed the expected pattern for poor hearing, with minimal stapes displacement. When applied to Youngina capensis, the results were remarkable. The simulations revealed that Youngina's stapes exhibited displacement patterns similar to those of modern geckos and other reptiles with tympanic hearing systems. The bone showed strong responses to frequencies between 100 and 1,000 Hz, indicating sensitivity to airborne sounds rather than just ground vibrations. Modern geckos typically show peak hearing sensitivity between 400 and 1,000 Hz, and Youngina's predicted hearing range falls squarely within this spectrum. The frequency range that Youngina could apparently detect includes many biologically relevant sounds. The rustling of insects in leaf litter, the footsteps of small prey animals, the movement of potential predators, and even low-frequency vocalizations would all have been accessible to this ancient reptile. The research also reveals the mechanical innovations that made advanced hearing possible. The evolution of a slender, flexible stapes was crucial, but equally important was the development of the annular ligament, a ring of flexible tissue that allows the stapes to rock back and forth within the oval window of the inner ear. Computer simulations showed that even primitive reptiles with bulky stapes could achieve significantly improved hearing if their ear bones were suspended by flexible ligaments, rather than rigidly attached to surrounding skull bones. The implications of this discovery fundamentally challenge how we understand reptile evolution. If Youngina capensis possessed advanced hearing 260 million years ago, it suggests that this capability was present in the common ancestor of all modern reptiles. This would mean that lizards, snakes, crocodiles, and turtles all inherited their hearing abilities from a shared ancestor rather than evolving them independently. This single-origin hypothesis is far more parsimonious than the multiple independent evolution scenario that has dominated scientific thinking for decades. The timing is particularly significant. Youngina lived approximately 8 million years before the Permian-Triassic mass extinction event that would eliminate over 90% of marine species and 70% of terrestrial vertebrate species. The research team employed additional analytical techniques to support their findings. Using a phylogenetic flexible discriminant analysis with data from 104 modern squamate reptiles, they found that Youngina's stapes morphology clustered with species known to possess tympanic hearing. This suggests that the late Permian world that Youngina inhabited was filled with airborne sounds, that these reptiles could detect and interpret a level of acoustic communication and environmental awareness that previous reconstructions have entirely missed. The methodological breakthrough demonstrated by this research opens new avenues for investigating sensory capabilities in extinct animals. The same techniques could potentially be applied to other fossils, revealing the hearing abilities of dinosaurs, early mammals, and other prehistoric creatures. We may discover that sophisticated senses evolved much earlier and more widely than current evidence suggests. Traditional paleontology relied on morphological comparisons and educated speculation about function. Modern computational methods allow researchers to test functional hypotheses directly, transforming fossils from static museum specimens into dynamic sources of behavioral and physiological information. This research represents a fundamental shift in how we understand extinct animals. Rather than viewing them as simplified versions of modern creatures, we're beginning to appreciate that they possessed sophisticated capabilities that allowed them to navigate complex environments. The story of Youngina capensis serves as a reminder that evolution often innovates earlier than we expect. Complex traits that we associate with advanced animals may have much deeper evolutionary roots than previously recognized. Youngina capensis has been silent for 260 million years, but science has finally given us the tools to understand its acoustic world again through biomechanical simulation. In doing so, we've discovered that the capacity for hearing, one of the most fundamental senses that connects animals to their environment, evolved much earlier than we thought possible. What other secrets are waiting to be unlocked in the fossil record? What other assumptions about ancient life will future discoveries overturn? The story of Youngina reminds us that in paleontology, as in all science, we must remain open to the possibility that our current understanding represents just the beginning of a much larger and more fascinating story.